This is FET220 computer system. Which of the following is the list that arranges A through D in order of effective access time of main memory from shortest to longest? Here we have the table with cache memory, main memory, and some of the implementation that we use, so whether it will use cache memory or not, and also the access time as well as the hit ratio. Here we have a possible list of the effective access time of main memory, and we need to put these in the correct order to see which one is the answer we want. Access refers to reading and writing data, and the time from placing an access request until the result is returned is called access time. In order to bridge the difference in the processing performance of the CPU and the access speed of main memory, a cache memory that supports high-speed access is placed between the two. The hit ratio is the probability of existence of the target data in the cache memory. If the target data does not exist in the cache memory, the data is read from the main memory. But if the hit ratio is p, the probability of the data being in the main memory will become 1 minus p. Let's just create a brief sketch of what this looks like. Firstly, we have our CPU, which is going to call the instructions from the memory that we need to retrieve. If a value is needed from memory, it will first go to the cache memory. This is a very high speed, yet expensive piece of memory. Memory is sometimes drawn preemptively, but also stored post using any function. If anything needed from memory or any data is inside the cache, it will straight away be returned, sometimes within 1 or 2 clock cycles. However, if it is not in the cache, we will need to access main memory to retrieve it and place it into the cache. So here we have our main memory block, which is normally a lot larger. If we then access this, it takes a lot longer to retrieve the data, so it is preferable for memory and data to be stored in the cache. However, it's too expensive and not viable to have all memory as cache. This is why we have this daisy chain kind of setup. So if the access time of cache memory is TC and the access time of main memory is TM, the effective access time is going to be TC times P, which is the probability of the data being stored in the cache, plus TM times by 1 minus P, i.e. the time it takes to access main memory times the probability of the data not being stored in the cache. Based on the values of each operation, the calculation is performed as below. Order A. TC is equal to 0, TM is equal to 15, and the probability is equal to 0. The effective access time is therefore TC times P plus TM times P minus 1 minus P, as we've described up here. As the cache access time is 0, in this case, we just simply have all access to main memory. This means it's going to take 15 nanoseconds per try to access, so 15 times 1. So the effective access time is 15 nanoseconds, i.e. directly equal to the time to access the main memory. Order B. Again, our access time to cache is 0, as we're only accessing from main memory. Here, the main memory access time is 30 nanoseconds, and the probability of data being stored within the cache is 0. Here, we can use the same equation that we did on the previous slide and how we derived it. And this is equal to 0 plus 30 times 1, which is equal to 30 nanoseconds, i.e. the effective access time is again equal to the time it takes to access main memory. In order C, we have now a cache access time. Our cache access time is 20 nanoseconds. Our main memory access time is 70 nanoseconds, and the probability of a data being stored in the cache is 0.6. We then use the formula from the previous slide, which we also derived, and this is equal to 20 times 0.6 plus 70 times 1 minus 0.6. And this works out to be 40 nanoseconds. So you can see that this is greater than the cache access time and also less than the main memory time. This is a condition that is always a good check when calculating the effective access time. Finally, order D, Tc is equal to 10 nanoseconds, Tm is equal to 80 nanoseconds, and the probability of a data point being stored within the cache is 0.9. Here we follow the same calculation, and then we work this out to be 17 nanoseconds. We can do the check again that our effective access time is within the bounds of the cache access time and the main memory access time, and this holds. Therefore, we can put our shortest to longest effective access time in order. Here we have A, D, B, C, based on the values of each option. C follows the order of shortest to longest effective access time. Therefore, C is our correct answer. And here we can see our answer is C. And in this video, what we've learnt is how to calculate the effective access time, and also what this means within the processor, and how the probability of a data point being stored in cache affects this.